Hello and welcome to the second module on big data. So as we saw earlier that the variety and volume of data requires us to have a new paradigm for handling all the computing, right? And one of the most popular paradigm that's used for handling big data computation is MapReduce. So this was a programming model that was pioneered by Google, which were using initially a proprietary implementation, but later on Hadoop, an open source platform that implements MapReduce, became really popular. Right? And so in the next few slides, I'll give you a very brief introduction to MapReduce. So MapReduce, as we will see, is a very intuitive approach to parallelize computation, typically on commodity hardware. But the big problem when you're especially using commodity hardware, is that machines tend to fail a lot, right? So fault tolerance becomes a big problem. So for example, Google runs typically 1 million machines in one of their data centers, and assuming on an average 3 years lifetime for one machine, you would expect about 1,000 machines to fail per day. So Hadoop is a distribution framework that fundamentally uses MapReduce as the computing paradigm, but on top of it, it takes care of data distribution, communication, and fault tolerance, and makes it very convenient to use this kind of a distributed setup in solving everyday problems. And hence Hadoop has been widely deployed commercially, and variants of that are continuing to be uh, very popular even today. So let's look at the MapReduce computing model. So the MapReduce, as you can imagine, consists of two stages: the map stage and the reduce stage, and in between there is a group and redistribute phase. So in the map stage, so the each mapper which runs on an individual machine takes a block of the data that you have to originally process, extracts some information from the data, and output these as key value pairs. Right. So the key, as you know, is an identifier. The value is any value that you would like to send along with the key. So we'll look at examples later. Right. And then before sending to the reduce stage, you sort and shuffle all of these key value pairs and you group them by the keys, so that all the pairs which have the same key value will go to the same reduce stage. And the reduce stage, you can compute aggregate statistics corresponding to the key. Right? You could add things up, you could summarize them, you could transform them, you could do any kind of filtering that you want based on the key. Whatever it is, you can compute aggregate values based on the keys. So here is an example of a very simple word count. It's like the hello world of the MapReduce programming. So let us say that you have a document. So what you would do is you would divide the document into different blocks as shown here, right? So the first block I have colored it red, the second block green, and the third block blue. And you send it to the different mappers. So what the mapper does is it reads each word in the document and then outputs that as a key, and the value is the count of the word in the document. So every time it encounters a word, it's just going to output it as that word with a count of 1. So the red mapper is going to output concept 1, off 1, and then the green mapper is going to output a variety of things. So in this case it's going to say for 1 and concept 1, and the blue mapper again outputs for 1, various 1, weighted 1, and so on and so forth. So in the group stage, what happens is you group things by the keys. So all the key value pairs which have concept of the key get grouped and they are sent to one reducer. Likewise, all the key value pairs which have for as a key, get group, and are sent to another reducer, and so on and so forth. And finally, the reduce stage aggregates all these counts regardless of which mapper they come from, right? And then outputs the total count. So in this case, you would get concept is 2 of 1 for 2, various 1, and weighted 1. It's a very simple way of doing word count, and your document could be very large. As long as you have sufficient number of machines, you can compute this very efficiently. It's not only in working with documents and other things, even simple items, even simple computation which you would have thought was straightforward, right, can become complicated when you're dealing with it at scale. So here is an example. I would like to compute the degree of a node in a graph. On very large graphs, computing even degree of a node becomes a little harder. Why is that? Because the data itself is not available to you at one time. Suppose I'm trying to build a graph of who called who. So I'm going to get things like A called B at time t and spoke for m minutes. So that's an event that will arrive to me after the call has finished. So at no point of time do I have all the calls of A stored in some place, and I'm just going to find the degrees. It's not like a single graph that's already been constructed for me, right? Or you could think of trying to create some kind of an interaction graph on Facebook. So user X posted on the wall of user Y. Now these events, even if they are available to you post facto, they are so numerous that aggregating them and to finding the degree of the graph itself could take a while. So you could actually use MapReduce to efficiently aggregate the edge events into a graph. Here is a simple program that would do that. So the mapper essentially takes each edge event, right? Each event, each interaction could be the posting of a message on Facebook, could be the making of a call. It takes each of those events and then it creates two key value pairs for every event. That has of A called B, it will say okay, A1 and B1. And the reducer essentially now takes in every event or every key value pair that have the same key. That essentially means it's going to gather all the node A's, add up the events corresponding to node A, and it will output the degree of node A. Fairly simple, fairly straightforward. And so you don't really have to create an adjacency matrix or an adjacency list representation of your graph to be able to answer queries like degree. You can stick with the edge list representation and still answer these kinds of queries. Right? So let's look at some other questions that not necessarily need MapReduce but become harder when you're looking at large data. So we looked at k nearest neighbors in one of the earlier modules. Right? So how would you find k nearest neighbors if you have huge volumes of data? So linear search is impossible, right? Because any index sector should be small enough to fit into memory for you to do linear search. That's not going to happen if the data is very large. So that's a new approach for finding neighbors in data called locality sensitive hashing, introduced by Andre Broder and others. So the basic idea here is to find hash functions. So you remember hash functions? They are functions that take a key as an input and then they hash it into one of n buckets, right? So here what we do is we want to find hash functions such that two elements x and y, if their distance is less than a certain threshold, they hash to the same bucket or same bin. Two elements x and y, if the distance is greater than a certain threshold, then x and y hash to different bins. And we would like this to hold with very high probability. Right? We would like this to hold for sure, but then it's hard to get something that will work always. So we would like to hold for this to hold with very high probability. So now if I want to find if y is the nearest neighbor of x, then all I need to do is look through the bin into which x hashes. Right? And since this is only with a very high probability, right, so you might actually miss your nearest neighbor, but you will certainly get some neighbor that is close enough, because since the data set is large, even close neighbors are usually sufficient. So depending on the kind of distance function that you want to use on your data, if you remember, we talked about different distance function in nearest neighbor. Depending on the distance function you want to use on your data, you're going to have to define different hash functions. And so for example, if you want to look at distance measured between sets such as groups of words and so on and so forth, you would probably like to use the Jaccard distance, which is 1 minus the size of intersection divided by the size of union, right? Or you could use the Euclidean distance between points, or between vectors you could want to use the cosine distance. And for all of these, people have worked out what are appropriate locality sensitive hash functions. So I'm not going to get into the details of the locality sensitive hashing, just wanted to give you a feel for how hard things can be when you are looking at large volumes of data. Even what you thought are simple operations become harder when you're looking at large volumes of data. Here is another example. We talked about frequent pattern mining and association rule mining. Imagine counting frequent items in Amazon's transaction data. You have millions of transactions a month, so just blindly running a priori is just not going to work. So we need a different approach to the problem, right? We can still use the a priori property, but we have to think of how you would handle the memory more efficiently. So here is a very simple approach to do distributed counting. You divide baskets randomly among compute nodes, right? So here we are talking about market basket data, right? So essentially what I mean here is the transactions are randomly divided among all the nodes that you have, right? You run a priori in each computing node separately, and whatever turns up as frequent item sets in each of those nodes are now candidate frequent item sets. So what you have to now do is go back and count the actual frequency of this candidate item sets, because the original candidates were determined on a small subset of the data. You will have to go back and count the frequency on the entire data to determine if these candidate sets are frequent, right? So remember that when you are doing this in the distributed fashion, the threshold that you are using for defining frequent item set should be lowered. So if you are splitting your data 10 ways, then the threshold that you had for frequency should be lowered by 10 times, right? So once you have these candidate frequent item sets, you don't have to count it in a single machine. You could still do this in a distributed fashion. So again, each node will count the frequency of just this one candidate item set, and then at the reducer you could basically combine the frequency of frequency reported by each node, and then report frequency of the item set on the entire data, right? So there are other computing models. I just spoke about MapReduce in this talk. There are other things as Spark, which is a MapReduce variant with local memory, and then there are GPUs, which are multi-core massively data parallel computations, and then there are other models with shared memory multi-core computations. So depending on what is the use case that you have, you will have to use different computing models. It's not that MapReduce is a one solution fits all method. So depending on the solution, depending on the problem that you have, you'll have to pick the computing model that best suits you. Right? So one thing which I would like to point out is that data visualization is still a challenge for big data, right? So visualization is a challenge for normal data analytics, but it is a challenge for big data. So people are working on adaptable interfaces or interactive visualization, but more often than not, people are still trying to fit old visualization ideas to big data, and that is not working. So it's a very, very active area of research, and several new generation methods are needed here. I just wanted to draw your attention to the fact that here is something that people could work on. Right. So in summary, data analytics has matured to a certain level, and so now people are looking at big data challenges. So in some sense, evolving to a new discipline of data science, where just the analytics techniques are not themselves sufficient, but we need more understanding from the modeling front. It's a very exciting time to be in this space. Availability of vast amounts of data, and the Internet of Things hype picking up. There's going to be a lot more data available. New computing models that could very well be a high impact on society if you're able to come up with solutions to handle, make sense out of this big data. So that brings us to the end of this module.